And we're live. Excellent. Okay. I need to fix my camera. I had a little small technical issue with my camera, but I believe I have figured it out. But I wanted to make sure that I went live because I knew that I was a couple minutes late getting into this thing. So let me set this camera up while I am doing my preliminary information with you guys. It looks like there's about 10 or 11 of you so far. Hopefully that number will be more. But here we are. Here we are on a snow day of some sort. It's weird. I mean, it's not much snow yet. Oh, hold on. Haha. Hold on, now I can fix this thing up. There we go. Hold on. So tell me, who is here? Hello, everyone. You need to be leaving a comment in the chat so that I can see who is here. I'm just setting up my camera, as you can see. Oh, and my rubber band broke. That's fun. I have another one in here. But I'm setting up my camera so I can do the top-down visual of this thing. Here we go. Rubber band. There we go. Now you're in place. Good. Then I can do this. Come on, there we go. And boom, we got light. Let's move that cord over there. There we go. And there are all those wonderful people saying hello in the chat. Looks like there's only, what, 7 of you so far, but there's 11 people viewing. I don't know what that's about. People need to be letting me know whether or not you're here or something. So yeah, what a snow day it's been so far. Supposedly we're going to be getting snow and snow showers for the next bunch of hours or something. Let's take a peek back here. It's starting to come down a little bit, like very finely or something along those lines. Oh, hold on, there's a knock at my door. I think it's unlocked. Hold on, I have to go get the knock on my door. Give me a second. Hello? Hi. You want to come say hi?
I want to watch something.
Well, come say hi. Come say hi to everyone real quick. Okay. Oh, there was a knock at my door. And the knock at my door just so happened. Wide shot. You want to say hello? Hold on. Let me see. Put this back on right here. This was the knock at my door right here. This little one. Hey, look at the camera. You want to look at the camera? There she is. No? You want to say hi? You say hi right there. You want to look at the cat? Okay, go look at the cat. Okay, top down. There we go. That was my daughter. So, she wanted to go talk to the cat. Apparently, because the cat likes hanging out in this room, because it's a bit more private throughout the day when the kids are running around the rest of the house. Yeah, so that's where we're at. Okay. I'm going to have to let her out the door. My daughter, not the cat. Yeah, I'm going to have to let her out the door. So give me one moment, and then we will get started. But I will give you a couple of reminders. Number one, there are 2 PDFs in the Google stream from last week, from last Friday that I posted. I posted them on the 29th, PDFs 6.5 and 6.6. I'm going to be working off of those, and I am going to ask that you have those notebooks out and open. Give me 1 second while I have my daughter vacate the room. Ellie? Ellie, babe, you gotta leave.
No, I want to watch something.
I have to get work done.
But I want to watch something.
But my students are on the computer. Give me kisses.
I don't want to watch something in the computer.
Okay.
I want something in Mom's phone.
You gotta talk to Mommy about that.
Okay.
Minus 10 points to all of you for not commenting on my daughter being the cutest thing that has ever existed. How dare you? I'm just saying. And if you tried now, it'd be like, nope, too late. You never said it the first time. So, Oh, yes, but here we are. So, ladies and gentlemen, last Friday we continued with the second half of Chapter 6, simplifying radicals, and we're going to continue with more of that today and build upon what we've already done. Again, this is not my normal setup. I have not been in my classroom since Friday, so I don't have all of my normal materials, but this is what we got. So I am going to call this Simplifying Radicals Continued, and today is Groundhog Day. For those of you that know the reference to the movie Groundhog's Day. I'm just saying you should. Anyway. Let's see. 1, 2, 3, 4, 6, 8, 9, 10, 11, 12. Alright, so I see 12 unique commenters in the chat, yet there are 14 people who are viewing. Like I said, if you haven't left a comment, please make sure that you do so that we're all on the same page here. Last class, I did some basic examples of simplifying radicals. I'm going to review a couple of the earlier ones, just so we're all on the same page, and then I'm going to get to some of the more difficult ones, and then we're basically going to keep building and building and building and see how far this kind of goes. So, example number 4. Example number 4 is the negative fourth root of 405. Now, for the sake of argument, the negative is on the outside, and you can assume that that is a negative 1 that is being multiplied by that radical. You can assume that that is a negative 1. Let me fix my little camera here. Click. There we go. My beautiful face right there. There you go. You got me. There you go. Anyway, that negative is on the outside, so you don't have to worry about getting errors in your calculator or whatnot. I do have my calculator right here. I don't have my calculator that I typically have on my computer, but that's okay. I'm going to follow the same procedure that we did last Friday. Last Friday, when we began going through these problems, I took the number 405 and I began breaking that thing apart. Clearly, it cannot be divided by 2, so I'm not going to bother. Instead, I believe it can be divided by 3. Yes, it can. It can be divided by 3 again. It can be divided by 3 again. It can be divided by 3 again. It was divided by 3 4 times, and I was left over with a 5. So just to double check, yep, 405. Break it down into its prime factorization would be your best bet. So this would really be the negative fourth root of 3 times 3 times 3 times 3 times 5. Again, there's more than one way to do this problem, but I just want to show you the most straightforward way based on what we did last Friday. Now, this is a fourth root, meaning that in order to escape or simplify out of a fourth root, you must be a perfect fourth power. Well, I can make a fourth power right there. That is 3 to the fourth power. Now, just for the sake of argument, I'm going to kind of break this thing apart like this. Doing this slightly different than what we did last time, just to kind of exemplify what's happening. I am allowed to break apart a radical under the operations of multiplication and division. Let me repeat that. I am allowed to break apart a radical under the operations of multiplication or division. I am not allowed to break it up under the operations of adding and subtracting. I am not. Here I am, And I use multiplication, of course, because there's multiplication separating all those. The fourth root of 3 to the fourth, they cancel each other out. Let me put that in red so you can kind of see the contrast here. This fourth power cancels out with this fourth root. And now when I say it cancels out with the fourth root, that radical symbol is a part of the root. So this becomes -3, because the power and the root go away, times the fourth root of 5. And that would be the simplified answer. There's more than one way to do a problem like this. There are shortcut ways to do problems like this. But in my opinion, this is the most straightforward way of going about it. Let's try another one. Now I want to try another one, but I want to try it in a slightly different kind of way. Let me just double check to make sure that the number works the way that I want it to. Okay, yeah. Let's do it in a slightly different kind of way. So I'm on the 6.5 worksheet still, and I'm looking at a problem like number 5. Example number 5, which is the third root of -5,000. Now I'm going to do this in a slightly different way, simply based on what I recognize about the number 5,000. Without writing anything down yet, hopefully we can recognize that 5,000 is a combination of 5 times 1,000. Not a big deal there. But the number 1,000 is a perfect cube. 10 cubed is 1,000. 10 times 10 times 10. Now, I could break this thing down as far as it could possibly go. I could, literally do, okay, 5,000 divided by 2, divided by 5, divided by 5, divided by 5, divided by 5, divided by 2, divided by 2. I could break that down like we did before. But instead of doing it like that, sometimes we can recognize perfect cubes. 1, 8, 27, 64, 125, 216, 343, 512, 729, 1,000, all of those are perfect cubes. Sometimes we can recognize them. And if you can recognize a perfect cube, watch how I break this thing apart. I can break it apart like that. Now, -1, as we discussed last Friday, -1 by itself is a perfect cube. You can take -1 and cube it, and you get -1. -1 you can take out of odd roots. You can take them out of odd roots just as a -1. So I break that apart. That is a special case. 1,000 is a perfect cube. 5 is stuck. This is just a shortcut way of looking at it. But again, it depends on whether or not you recognize these perfect powers. It's whether or not you recognize these perfect powers. Recognizing these perfect powers comes into play with a problem like number 6. Number 6 is the fifth root of -1215. Now, you don't have to memorize perfect powers. You don't have to memorize them. But you have to recognize them when you get them in the calculator. So, watch this. 1215. Clearly, it's divisible by 5. And then I get this 243 number. With a little bit of digging, you can recognize that 243 is 3 to the 5th power. It doesn't take that long to figure out that 243 is 3 to the 5th power. You just keep dividing it by 3 until you can't anymore. It's, well, 3 times 3 times 3 times 3 times 3. 243. There are 5 of them. Equals the 5th root of -1 times the 5th root of 3 to the 5th times the 5th root of 5. Instead of doing the prime factorization, instead of writing out all the numbers, the bulk of the work is done in the calculator, recognizing that, well, 243 at 243. 243 times 5 is 1215. There's that -1, which again, odd root. It's an odd root. Watch this. There's a 5th root. Or you could do it like this with a 5th root. 5th root of -1 is -1. Odd roots. Negative, well, 1 times 3. 5th root of 5. These problems are all done in a slightly similar way. Let's do one with a variable. Let's do one with a variable, and then I want to do one that's a bit more complex. You'll see. You'll see what I'm referring to when I say complex. Again, I'm on that worksheet, and I would like to try number 10. Example number 10. Again, these problems are going to get progressively more difficult. Okay. I want to talk about this one. First, 45. This is a square root, and 45 is not a perfect square. Now, 45 is hiding perfect squares, which we'll break down in a moment. X to the 3rd power. Well, that's not a perfect square, but I could break up that x. Y to the 8th. Well, I could do something with that 8, but again, I'd have to break that thing apart. Here's what we can do. First, recognize what you can do with 45. I know 45 is divisible by 9. Yep, and you just get a 5 left over. 9 times 5. 9 being the perfect square, the largest perfect square. 5 you can't break up any farther. So immediately, you could break up that 45 to be like that. I still have to deal with the x and the y, but again, we'll deal with that in a moment. X to the 3rd power, I'm going to have to break this thing up. X to the 3rd power, x times x times x. I could put 2 of them together to be a perfect square. This could be the square root of x squared and the square root of x. Again, breaking it all up by multiplication. The y to the 8th is a slightly different tilt to it. Y to the 8th. You could break up that y to the 8th. Again, and I'll show this kind of visually, if you can kind of see me in the corner right here, my little visual thing. I got 8 right there. And I could break it up. You know, there's a those 2 for a square, those 2 for a square, these 2 for a square, and these 2 for a square. So I'd have 1, 2, 3, 4 different ones being square. I could do that. Another way of potentially doing it is recognizing a different type of property. And the different type of property that I could do here is this. There should be a square root around that y to the 8th. There should be a square root around that y to the 8th. But instead of writing it as a square root, I decided to write it as a 1/2 power. It's the same thing. Remember, when you have a fractional exponent, you need to remember the phrase power over root. It's a little bit of improvisation, yes. There's no one specific way to do this problem, but it's a way that helps get the answer a lot quicker. Now, I'll deal with that in a moment. Let's just bring things down piece by piece. Square root of 9 is clearly 3. The square root of 5 has to stay the square root of 5. The square root of x squared just becomes an x. The square root of x just stays the square root of x. And because I was able to recognize, okay, y to the 8th would have a square root around it, that would be a 1/2 power, I am allowed to multiply those two exponents together. It just allows me to bypass a lot of extra work. 8 times 1/2 is just 4. Now, I'm not done yet, but this is, again, one way you could handle the problem. Trying to give you a little bit of a shortcut. Ultimately, the way that we would write the final answer would be that. Because the 3, the x, and the y to the 4th all were able to get out of that square root, so I brought them all together. They're all being multiplied together. Again, you're allowed to do this if you have multiplication or division. And the square root of 5 and the square root of x, well, I can bring them back together to make the square root of 5x. You can break these things apart. You can put them back together. That's what these things are all about. You can break them apart. You can put them together. That leads me to the next example, which is going to utilize that idea of either putting them together or breaking them apart. It's going to utilize a little bit of everything. So I'm still on that worksheet. I'm still on that worksheet 6.5. And I'm looking at a problem. Specifically, I'm looking at number 17. I'm looking at number 17. And number 17 has this. And I want to talk about what the heck is going on here. Okay. And they want you to simplify it, of course. Let's recognize a couple things. First, there's multiplication separating the parentheses. And there's multiplication separating the coefficient and the square root. Multiplication across the board. Okay. Let's recognize something else. 24 is not a perfect square. It is hiding a perfect square, but we'll deal with that in a minute. 18 is also not a perfect square, but it may be hiding a perfect square. The 2 and the 7, I'm not really sure what to do with them. Here's what you could do. One good idea of handling this problem is putting everything back together first. And what I mean by that is this. All of these terms are being multiplied. In fact, because they're all being multiplied, the parentheses don't really matter. If there was addition, subtraction, then yes, the parentheses would matter. But since they're all being multiplied together, let me just bring them together like this. 2 times 7 is 14. I just multiplied them together. 24 times 18, I can bring them together underneath the same square root. See, because when you have 2 square roots, they are the same type of root being multiplied together, I can put them back together. As we learned last Friday, you can take a radical, no matter what the type of root it is, and you can split it apart. If it's like a 4th root of some number, you could break it apart, 4th root and 4th root. On one of the previous examples that there we go. We just did right here. I was able to take these terms within the 4th root, and I was able to break them apart to 2 separate roots using multiplication. In the exact same fashion, I'm allowed to take these 2 square roots and put them back together underneath a square root. Now, 432, I don't know exactly what to do with 432, but now it's a brand new problem. Now it's a brand new problem. Now I can... Reconnection successful. Okay, that was odd and strange. Alright, I really hope that worked. Just as a side note, did anything get messed up? I don't think that it did. Yeah, I don't think that it did. Alright, back to this. So that's 432. What do I do with that 432? I'm going to divide it by 2. 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 And I can't divide it by 2 anymore. How many times did I do that? 1, 2, 3, 4. I divided it by 4. Okay. And then I got a 27, which is 3 squared. Or cubed, I should say. Yeah. So 2 to the 4th times 3 to the 3rd. 432. Okay. Again, prime factorization. Breaking that thing down as far as it can possibly go. In fact, you know what? I'm just going to break it down like this. I'm just going to do 2 times 2 times 2 times 2 times 3 times 3 times 3. There we go. And I just showed that in the calculator right there. I'll just do it again. 432. It's a square root. Square root means that I'm going to need 2 of them in order to escape. That's a 2 squared, a 2 squared, and a 3 squared. This becomes 14 times 2 times 2 times 3 times the square root of 3, which is not allowed to escape. I'm going to show you an alternate way of doing this problem in a moment. I will definitely show you an alternate way of doing this problem in a moment. Just because it'll get you the same answer, I just like the alternate way. 14 times 2 times 2 is 3. 168 times the square root of 3. Yeah, I'm definitely going to show you an alternate way. I want to show you an alternate way simply because there is always more than one way to do this problem. As I mentioned on Friday, there is always more than one way to get to Tom's River. Parkway, Route 9, walking, jumping from tree to tree. It doesn't matter. Some ways are easier than others, but all of these ways will eventually get you to your goal, which is getting to Tom's River. Let me show you that alternate way, because I do like seeing more than one way to do a problem. And I'm actually going to label it in my notes as alternate way. So this is number 17, alternate. It's going to get us the exact same answer. I just wanted to show you that alternate way. And the reason why I wanted to show you that alternate way is because there is a way to do this problem without a calculator. There is a way to do this problem without a calculator. 24 and 18. Let me do this first. Instead of putting them together first, let me try to simplify them down as much as I can, because simplifying this thing down may be in my best interest. 24 could be broken up square root of 4, square root of 6, because 4 times 6. And 18 can be broken up square root of 9, square root of 2, because, well, 9 times 2. And what that gets me is, well, I'm going to have to multiply 14 times 2, square root of 6 is stuck for now, times 3 times the square root of 2, which is stuck for now. Just breaking this thing down. I'm going to show you, oh, actually, you know, I'll do it in red so you can see it a little bit better. Watch this. The 24's journey. 24 went here, and then it split apart. Square root of 4 became 2. Square root of 6 just stayed the same. The 18 broke apart. And you can see that 3 coming down. It's kind of like a little flow chart going on there. The 2 and the 7, they just multiplied together at the beginning and became that 14. And they're going to, well, they're going to change now, but, you know, they were a 14 for a while. 14 times 2 times 3. That should get me, I want to say 84. Yeah, 84. 84 times the square root of 6 times the square root of 2. Now, in reality, I'm not done yet because I can still simplify this down. I'm supposed to be getting the exact same answer as before. 6 times 2 is 12. And the thing is, well, the 6 is actually made up of a 2 and a 3. And that's important because since it's made up of a 2 and a 3, it has an extra 2 that is going to make another perfect square. There's the 6, and there's the 2. So this 6 and 2 combined back together. There's that 6, there's that 2, but they combined back together. They made me another perfect square, which was a 2. That 2 comes out. 2 times 84 should give me 168 times the square root of 3. Again, this is just another alternate way of looking at it. You don't have to do it this way. You could just stick to this method if you wanted to. Multiply everything together, break it back apart, and then see what it gets you. This way may be a bit more writing. But I want you to be aware of there's always more than one way to do a problem. There is always more than one way to do a problem. Some ways take longer, but visually they make better sense. Some problems take shortcuts, like the one that I did before, earlier, the original way. Personally, I think that this is a shortcut. But by taking the shortcut, some people don't like it simply because, well, I didn't really understand how the shortcut worked, but this way makes a bit more visual sense to me. Sometimes that happens. I just want you guys to be aware of what you can and cannot do. Let me try one more like this, and then I am going to step it up a notch. Because I love stepping things up a notch. Okay. I'm going to backtrack a little bit to number 16, which was 3 third root of 15 and negative 4 root of 45. Okay, let's recognize a couple things here. This 15 is not a perfect square. It's 3 times 5. 45 is not a perfect square, but it's 9 times 5. 9 being a perfect square. Watch what I'm about to do here. Okay. Again, visually, let me show you what happened. The 4 and the 3 just came down to make that 12. The 15, I broke apart. The 45, I broke apart. That 9 is a perfect square. Square root of 9 is 3. So hold on. Let me show you where everything just went. The 12 clearly just came down temporarily. The square root of 9 became that 3 right there. And everything else just came down here. This 3 and 5 and this 5 came down to join into one singular square root. The reason why that is important is because now I have another perfect square. Negative 12 times 3 times 5. Let's see. Negative 60 times 3, negative 180. I know there's a lot of arrows floating around here, but I'm just trying to visually show you what the heck is happening. You don't have to do these arrows, clearly. I'm just showing you a progression as to where things are going. This -4 and 3 could be multiplied together to give you that -12. That -12 is just going to travel down the rest of the problem until ultimately it's being multiplied by other constants. So that -12 is taken care of. This 15, which is 3 times 5, and this 45, which is 9 times 5, the reason why I got the 9 there is because of that perfect square. But the remaining numbers, 3 and 5 and 5, they combine to make this single square root. 5 times 5 is another perfect square, so it comes out there, and that square root of 3 remains in the square root the rest of the problem. And these numbers end up getting multiplied. The alternative way of doing this problem, and again, I want to show you the alternative way, another alternative way of doing this problem. And do it. -12 square root of, look what I'm typing into my calculator, 675. That's not the answer, it's just another way of doing the problem. 675 can be divided by 5, 5, and then there's a 27. So 5, 5, 9, 40, 25. I'm just trying to figure out. Ooh. Nope. Yes. Here's what I figured out. Alternative shortcut. 675, after a bit of digging, is divisible by 225. 225 is a perfect square. -12 square root of 225 square root of 3. -12 times 15 times root 3. -180 root 3. That's an alternative way of getting it done. It's the same concept, clearly a lot shorter. But it relies on you recognizing that 675 is hiding the perfect square 225. I don't know that many people who would be able to recognize that off the top of their heads. I don't know that many people that would. Mr. Markey, would you? Of course I would. But that's me. Recognizing 225 as a perfect square hidden inside of the 675 makes the problem 1,000 times shorter and a bit easier to follow. But it does the same work. It does exactly the same work, just in a different way. Strange. Now, like I said, I wanted to take it up a little bit of a notch. Taken in a slightly different direction, and that direction is this. Number 18. This problem I really do want to focus on what is necessary for what you need to do with this problem. Okay. First, the big difference for number 18 is the inclusion of addition and subtraction. Unfortunately, you can't combine them. I know a lot of people that would immediately be like this. Check this out. They'd be like, okay, 810 plus 240 minus 250 gets me 800. The answer is the square root of 800. Which is a decimal, and then they would try to simplify the square root of 800. Hold on a tick. The square root of 800, are you kidding me? This is not the square root of 800. The square root of 800 is not the same decimal. The square root of 800 is not the same decimal. It's close, but it's not the same decimal. It's not the same number. You are not allowed to just simply combine these radicals the way that you want to because addition-subtraction. You are only allowed to combine and rip apart those radicals if you are multiplying, dividing. We have to come up with an alternative way of getting this problem done. And I have such a way. I have such a way of getting this particular problem done. Here's what we're going to do. First, I'm going to break this problem up to be the square root of 81 times the square root of 10. Are you allowed to do that? Yes, because multiplication. 81 times 10. Ms. Markey, why 81? Because 81 is a perfect square. 10 is just 2 times 5, so I can't do anything there. I'm going to leave it. Can't do anything with it. 240. Now, after a little bit of digging, there it is. After a little bit of digging, after like 10 seconds of digging, I can figure out that 240 can be broken up to be 16 times 15. And the reason why that is significant is because, well, 16 is a perfect square. And 15, well, 15 is just, what, 3 times 5? So I can't do anything there. But I can break that up to be the square root of 16 and the square root of 15. Oh, that should be a minus sign right there. There we go. What about 250? Well, hopefully it's fairly easy to see that 250 is divisible by 25. Takes a little bit of digging, but that digging doesn't take too long. Now, why is this significant? Well, let me simplify those perfect squares. This is 9 root 10 plus 4 root 15 minus 5 root 10. Okay. Well, because square root of 81 is 9, I can actually show that here. And the square root of 16 is 4, and the square root of 25 is 5. And then the other radicals just come straight down. Well, why is this helpful? Let me show you something here in my calculator. Check this out. 9 square root of 10. Notice I closed the parentheses around the 10. Minus 5 root 10 is equal to this specific decimal. Notice what I just typed in is the exact same decimal. Technically, these two terms, 9 root 10 and 5 root 10, are what we call like terms. They're like terms. Mr. Markey, I thought like terms, they had to have, what, the same variable and the same exponent. Yes. Variable, it could be the word variable, it could also be the word base. They would have to have the same base and the same exponent. Well, a square root is an exponent. A square root is the exponent 1/2. And 10 is the base. See, these two terms right here are no different than 9x minus 5x. If I said, hey, what's 9x minus 5x? You would say 4x. Yes, it would be 4x. Okay, I have 9 square roots of 10, and I'm subtracting 5 square roots of 10. How many square roots of 10 do I have left? Oh, well, you have 4 square roots of 10. Yes, you do. Addition, subtraction doesn't work with putting them together or ripping them apart. That's not what this is. Addition, subtraction, you can't put them together like that or rip them back apart. You can't do that. But you can combine like terms. Combining like terms is a process that you have used with variables, but it's a process that is used with adding and subtracting. In this case, combining those two, 9 root 10 minus 5 root 10 gives you 4 root 10. Oh, Mr. Markey, what about the remaining part? You can't do it. The remaining part, the 4 root 15, sorry. That is the simplified answer. As awkward and unfortunate and uncomfortable as that makes you, that is the answer. That's all that you can do to this problem. These problems are a process. They are a process. You got to trust me on that. We're going to get this process down. We will. Simplifying these things down, that is what is important. Now, again, this is when you are adding and subtracting these terms. You're going to follow a similar process to what we did before. You have to simplify them down individually until you find like terms. Individually until you find like terms, and then when you have like terms, you can combine them. This square root of 240, well, you could simplify it, ultimately finding that you don't have like terms, and it just comes straight down to the answer. I love these problems so much. Oh, goodness. This is called improvisational math to an extent, because with improvisational math, you have to kind of improvise what it is that you have to do, because it's something slightly different every time, depending on the situation that's in front of you. This is life. Life is when you wake up every morning and there's something different being thrown in your face, and you have to act accordingly. And every day you cannot act the same exact way. You can't. You can't do the same exact thing in the exact same fashion every single day. It's going to be slightly different every single time. I want to try... Oh, that's a fun one. Yeah, I want to try that one. I want to try number 23. Number 23. Number 23 is the following problem. Okay, different problem. Let's recognize what's in front of us. First, 2 sets of parentheses being multiplied together. We've faced problems like that before. However, here's the twist. There's addition subtraction in the middle. And because there's addition subtraction in the middle, we cannot proceed the way that we have in the past. We can't. So what do we do? Well, I would hope that you may be able to recognize the fact that this problem is a binomial times another binomial. Recognize the fact that this is a binomial times a binomial. This problem is like x plus 1 times x plus 3 or some junk like that. It's a binomial times a binomial. Meaning, you could FOIL this if you wanted to. Yeah, you technically could. You could technically FOIL this. You could do a weird form of distribution if you wanted to. You know what? I'm going to show you 2 ways to do this problem. I am going to show you 2 ways to do this problem. Okay, 2 ways. Let me get my pens out. There we go. Oh, I need my red pen. Come on, red pen. There we go. Got them. I'm going to show you two ways to do this problem. Here's one way of doing the problem. Actually, you know what? I need a little more room. I'm going to rewrite the problem. I'm just going to give myself a little more room at the top, but I am going to rewrite the problem in the same exact way. Square root of 5 minus the square root of 6 times the square root of 5 plus the square root of 2. There we go. Watch this junk. I'm going to show you two ways to do this problem. First, I'm going to take this entire parenthesis set, and I am going to distribute it to those two terms. And when I distribute it to those two terms, I'm writing this in different colors so that you can see the contrast. There we go. Between the two. You can distribute that square root of 5 minus square root of 6. Again, I'm going to show you an alternative way to do this in a minute. This is just one way of looking at it. And then you can distribute back. This may not be the way that I would do it, but this is one way of doing it. Now check this out. Square root of 5 times the square root of 5. Well, you could bring those together to become the square root of 25 minus the square root of 6 times the square root of 5. Well, that's the square root of 30 plus square root of 5 times the square root of 2. You could bring those together to be the square root of 10, square root of 6, square root of 2. Bring those together to be the square root of 12. And now all of a sudden, you are back to one of those problems where you have to combine like terms. Combine like terms. How am I going to combine stupid like terms here? Well, we got to see if we can simplify anything down. Square root of 25 is just 5. Square root of 30. Well, let's try to see what we can do with the square root of 30. 30 could be broken down. 30 is just this. There are no perfect squares inside of that 30. Okay. With 10, I know it's the same thing, actually. The square root of 10, I can't do anything there. But 12. 12, I could break that up root 4, root 3, so that's 2 root 3. As terrible as this problem looks, as terrible as it just seems, that is the answer. Most of the time, you would be able to combine like terms. Most of the time. But for this problem, they really did not give you much. Miss Marky, can't you do anything with the 10 and the 30? Nope. Unfortunately, no, you can't. It doesn't follow any of the rules that we've been learning. Can't simplify them, can't combine them. Let me show you the alternative way, and this is what I'm going to wrap up with today. Here's an alternative way of doing this problem. And the only reason why this works is because it is a binomial times a binomial. You could do a 2 by 2 box. Root 5 times root 5 gives you root 25. Again, you're allowed to do that because you're multiplying similar roots together. Root 5 times negative root 6, negative root 30. Root 5 times root 2 is root 10. And root 2 times negative root 6 is negative root 12. And once again, you would have to either combine like terms or simplify things down. The square root of 25 is just 5 minus root 30 plus root 10 minus, and again, you could break that thing down to be root 4 root 3. Gives you the same exact answer. Just an alternate way of looking at that problem. Okay. Couple of things. Number one, if you haven't commented in the chat, please make sure that you do so. As always. I'm assuming that we will be back in school on Thursday. I assume we will be back on Thursday. Simply because, I mean, what's it snowing like now, huh? It's not really snowing at all. Tomorrow, I mean, I don't know. There's a small chance we won't be in school tomorrow. It's supposed to be snowing throughout the rest of the day, but I didn't see anything. Let's just assume we'll be back tomorrow as well. Whatever. But thank you for joining. By Thursday, I'm hoping to assign you guys some practice problems with this that you'd be able to turn into me. But we'll talk about that more on Thursday. So, in the meantime, enjoy your day, enjoy your snow, go out and make a snowman. That whole thing. Again, I'm still mad at all of you for not commenting on how beautiful and cute my daughter was. That was very mean of you. I will never forgive any of you. On that note, so long, everyone.